Welcome to the deep dive. If you've ever worked with those really big, large language models, like GPT-4, Llama 3, they're amazing, but wow, can they be slow?
They really can. That sheer computational power, it just leads to latency. Getting those answers takes time.
Right. So today, we're diving into speeding that up,
Yeah.
specifically looking at a technique called speculative decoding and a new optimization method called AdaSPEC. That's all about getting speed without, sacrificing the quality we expect from these models.
And speculative decoding, or SD, is a really promising way to think about this. The basic idea is delegation.
Delegation.
Yeah. Instead of making the huge model, let's call it the target model, MPDA, do all the heavy lifting token by token, you use a much smaller, much faster model, a draft model,
Okay.
little helper model.
Kind of. This spits out token predictions really quickly. Then, the big expensive VB code just needs to check those predictions, and it can check several at once in parallel.
So parallel checking instead of slow step-by-step generation. That sounds much faster. It can be much faster. But it all comes down to how good the little draft model is.
You mean how often its suggestions are actually accepted by the big model?
That's it. We call that the token acceptance rate, alpha. If the draft model keeps getting it wrong, the target model rejects the suggestions and has to generate the old-fashioned slow way.
Then you lose the speed advantage. So, the whole game is making that draft model a really good predictor of the target model, maximizing that alpha.
That's the challenge AdaSPEC is designed to tackle. How do you get that alignment right? Especially when the standard ways might not be optimal.
What is the standard way? How do people usually try to align these models?
Well, the go-to method is knowledge distillation,
Yeah.
KD. Think of it like a teacher-student setup.
Okay.
The big target model is the teacher, holding all the knowledge. The small draft model is the student. And KD is the process of transferring that knowledge.
Makes sense. Train the student to mimic the teacher.
But here's the catch. When you apply traditional KD to speculative decoding, standard KD tries to make the student mimic the teacher on everything.
Everything, like the whole vocabulary.
It typically works by minimizing the difference between their output distributions, often using something called KL divergence. It measures how different the predictions are.
So lower KL divergence means the models are more similar in their predictions.
Right. Traditional KD wants that similarity across the board, global fidelity. But for SD, we don't necessarily need the draft model to be perfect everywhere. We just need it to be right often enough on the tokens that actually get proposed and accepted.
So the goal isn't perfect imitation, it's maximizing that acceptance rate, alpha. It's a slightly different objective.
It is. And then there's the capacity issue.
The size difference, you mean?
Yeah, these draft models can be tiny compared to the target models, maybe 50 times smaller, sometimes even more. They simply don't have the capacity to perfectly replicate the giant model's knowledge across every single possible token.
So trying to force it to learn everything, including the really hard or rare stuff, is like setting it up to fail.
Or at least setting it up to be inefficient. It wastes its limited learning ability on tokens it might never predict well anyway, or tokens that are just inherently tough for a small model.
And that effort could be better spent elsewhere.
That's the key insight AdaSPEC uses. There's a huge variation in how difficult tokens are to learn. Trying to minimize the learning error uniformly on easy stuff and really hard stuff might actually hurt performance on the easy tokens the draft model could master.
Okay, so conventional distillation is too broad, potentially wasteful for SD. AdaSPEC aims to be more selective.
Exactly. AdaSPEC stands for Adaptive Selective Distillation. It brings in this idea of selective token filtering to make the knowledge transfer more efficient for the draft model's limited size.
How does it do the filtering? What's the process?
It's a two-phase approach. Phase one is about setting up the filter itself.
Okay.
You start by creating what's called a reference model, where Umbeller, you just copy the initial draft model architecture, and then you distill knowledge into it from the big target model using a standard method, like the baseline DistillSpec.
So this map represents what a small model can achieve with standard, non-selective training, like a benchmark.
A benchmark, or maybe think of it as an identifier. It helps figure out which tokens are just fundamentally hard for any model of that small size to learn well from the target. It learns the hard-to-fit knowledge baseline.
Got it. So it flags the really difficult stuff.
Yeah.
Then what? Phase two.
Phase two is where you train the actual draft model, but you don't use the whole data set. You use a filtered version.
Filtered based on what the reference model learned.
Yes. You compare the performance, specifically the token-wise KL divergence loss, of the draft model being trained against the reference model. You calculate the difference, delta LWWW.
Okay, difference in loss for each token. What are you looking for in that difference?
You're looking for tokens where that difference, delta LW dollar, is large and positive.
Large and positive. What does that tell you? Why focus on those?
A large positive difference means the draft model currently has a much higher loss on that token than the reference model did. But wait, that sounds counterintuitive. Let me rephrase. We actually select based on the potential for improvement, focusing on tokens where the draft model can learn effectively compared to the reference. It's about identifying learnability. The paper looks at the difference relative to the reference model's performance to identify tokens the draft model can effectively target. Let me check the exact mechanism again. Okay, I misspoke slightly on the selection criteria earlier. The paper selects tokens where the reference model had a high loss, indicating difficulty for a small model baseline, but T, where the current draft model shows potential to improve. It's more nuanced. The actual paper focuses on the tokens with the largest positive difference in token-wise KL divergence loss, delta LWY, when comparing the draft being trained to the reference. No, wait, reading the outline again, the selection logic is tokens with the largest positive difference. Delta LWA are identified as highly learnable for the draft model compared to the reference model. My apologies.
Okay, let's stick with that. Largest positive delta L, W delta, means that token is identified as highly learnable for this specific draft model compared to the general baseline performance of the reference model.
Yes, that aligns with the source material. The reference model helps establish what's generally hard. By focusing on tokens where the draft model shows it can significantly reduce its loss relative to that baseline, high positive delta LW1 implies high initial loss but potential learnability demonstrated during training. You target the most impactful learning opportunities. You filter out the stuff that's just too hard overall and filter in the stuff that this draft model seems poised to master.
So you focus the training effort, maybe only on the top, say, 40% of these learnable tokens within a sample.
Right. Typically a fraction like K of 0.4 is used. You're essentially saying, let's not worry about the tokens this small model will always struggle with. Let's make it absolutely excel at the ones it can learn well. Optimize the limited resources for the biggest impact on the acceptance rate.
It's a targeted approach. So does this selective diet actually pay off in practice? What do the tests show?
They ran a pretty comprehensive set of experiments. They tested it on different kinds of tasks, things like arithmetic reasoning with GSM-8K, following instructions with Alpaca, generating code with MBPP, and text summarization on datasets like CNN Daily Mail and XUM.
A good mix. And what about the models themselves?
They used different pairings to test robustness. One was a small to large setup, Pythia 31M as the draft, Pythia 1.4b as the target, both from the same family.
Okay.
But they also did a medium to large cross-architecture test, CodeGen 350M as the draft model, and Phi2 as the target. Different model families entirely.
That cross-family test seems important. Does the technique still work if the models aren't closely related?
That's what they wanted to find out, and the headline result? Yes. AdaSPEC consistently beat the baseline, DistillSpec, which uses more traditional KD.
Consistently higher acceptance rates.
Across all those tasks and both model setups. The gains in alpha, the acceptance rate went up to 15% in some cases compared to the baseline.
15% is significant. Could you give a specific example?
Sure. On that GSM-8K arithmetic task using the Pythia models, DistillSpec got an acceptance rate of about 57.6%. With AdaSPEC, that jumped to over 62.6%.
That's a solid 5% absolute increase. And on something like summarization.
On CNN Daily Mail, again with Pythia, it went from about 73% alpha with DistillSpec up to over 74.2% with AdaSPEC. Smaller gain there, but still consistent improvement.
And crucially, does this higher acceptance rate translate into actual speed, faster generation?
Yes, that's the bottom line. They ran tests using the VLLM inference engine, a common tool, on an A100 GPU. The higher alpha from AdaSPEC directly led to speedups, generally in the range of 10% to 20% faster generation compared to DistillSpec.
So faster tokens per second.
Right, like on the MBPP code generation task, they saw tokens per second go from around 149 with the baseline up to over 181 using AdaSPEC. That's a noticeable difference when you're generating a lot of text or code.
Okay, so the numbers show it works. But why? What's happening under the hood? Why is being selective better than trying to learn everything?
They looked into that. One way is by analyzing prediction confidence. They measured something called the logit margin.
Logit margin.
It's basically the difference in the model's confidence score between its top prediction and its second best prediction. A big positive margin means the model is really sure it's right.
And AdaSPEC models had better margins.
They did. They showed more frequent high positive margins, meaning more confident, correct predictions. And importantly, fewer or less severe negative margins, which represent errors. So by focusing, the draft model seems to become more decisive and accurate on the predictions that count.
It gets more confident where it matters.
Mm.
Does this focus also lead to better overall alignment? Even though it's not optimizing for global alignment directly, like measured by that KL divergence metric.
Interestingly, yes. Even though AdaSPEC isn't explicitly minimizing KL divergence across all tokens, it consistently resulted in lower overall KL divergence between the final draft model and the target model compared to the baseline.
So being selective somehow leads to a better, tighter, relevant alignment.
It seems so. By mastering the learnable high-impact tokens, the draft model ends up being a better mimic in the ways that actually benefit the speculative decoding process. The alignment becomes more focused and effective.
And you could see this focus in the specific tokens it chose to learn.
Yeah, the case studies were revealing. For the GSM-8K arithmetic task, AdaSPEC overwhelmingly selected math-related tokens numbers, operators for its focused training phase.
It automatically identified the critical vocabulary for the task.
Precisely. It demonstrates that the filtering isn't arbitrary. It's learning to prioritize the knowledge that's most useful for the job at hand based on what it can realistically learn given its size.
That's pretty smart. One last thing. Scalability. What happens when the size difference between the draft and target model is enormous?
Right.
Does AdaSPEC still help?
That was a key finding. The advantage of AdaSPEC over the baseline actually became more significant as the size gap grew.
Really? So it helps more when the draft model is tiny compared to the target?
Yes. They tested gaps up to 64 times difference in size. In those extreme cases, being selective about what the tiny model tries to learn becomes even more crucial. AdaSPEC's ability to bridge that capacity gap shines through more strongly.
So wrapping this up, AdaSPEC basically acts like a smart tutor for the small draft model. It figures out what's just too hard to bother with, given the student's capacity, and directs all the effort towards mastering the achievable but important topics from the expert teacher model.
That's a good way to put it. It maximizes the utility of the small model's limited capacity. Filter out the noise, focus on the signal it can actually handle well.
And the result is a higher acceptance rate, leading directly to faster LLM inference without compromising the quality of the big target model.
Right. And maybe the final thought for you listening is this. Accelerating these powerful models might not be about creating perfect miniature replicas. Instead, it might be more effective to train these smaller assistants to be exceptionally good at predicting just the critical, learnable parts of the task. Getting 100% on the parts it can learn might be far more valuable for speed than getting, say, a 70% across everything.